Section: Introduction. In this section, we introduce our approach to data augmentation, which enhances the training set by creating virtual samples through random changes to the original data. This helps reduce overfitting when training large deep neural networks. However, creating an effective data augmentation strategy requires specific knowledge about the task, as different areas benefit from various transformations and their intensities. To address this challenge, we utilize Data Augmentation Search, DAS, which automates the customization of data augmentation for various tasks and domains. DAS methods work by sampling from an optimized policy that includes the likelihood of selecting transformations from a set, along with their strengths. The complexity of this search space makes optimization difficult. Differentiable DAS methods tackle this by using a gradient-based approach to solve a two-level optimization problem. The goal is to find the best augmentation policy that allows a neural network trained on the training set to perform well on a validation set. While previous methods have shown promise, they often limit the number of transformations to 2 or struggle with the order of transformations, leading to inefficiencies. In our work, we aim to optimize the augmentation policy across 4 key aspects: the number of transformations, their types, the order in which they are applied, and their magnitudes. We present FreeAugment, the first fully differentiable DAS method that optimizes all these aspects simultaneously using gradient descent, without relying on heuristics or greedy methods. FreeAugment achieves this by learning a probability distribution over the number of transformations, allowing for variable depth. It also optimizes the types and order of transformations by learning the probability distribution over their permutations, ensuring that no transformation is repeated. Additionally, we sample stochastic magnitudes for each augmentation from a learned probability distribution, which is refined through backpropagation during the search process. This entire framework is optimized on a validation set through a two-level optimization approach. Our experiments demonstrate that FreeAugment is versatile and effective across various domains, yielding results that are comparable or superior to existing methods on benchmarks involving natural images and other types of visual data. In summary, our main contributions include a novel method for jointly learning the number of transformations, a formalized approach to avoid redundant transformations, and evidence of the benefits of optimizing all aspects of data augmentation policies together, leading to state-of-the-art performance. In the related work, we note that previous efforts to automate data augmentation have often required significant domain knowledge and manual effort. Early methods, like used reinforcement learning to predict transformation types and magnitudes but were limited in efficiency. Other approaches, such as evolutionary methods and Bayesian optimization, also face challenges in learning effectively. While some recent methods have begun to explore differentiable DAS, many still restrict the number of transformations or rely on predefined sub-policies. FreeAugment stands out as the first to globally optimize the distribution of transformation permutations in a fully differentiable way. Section Summary. In this section, we introduce FreeAugment, a novel differentiable data augmentation search method that optimally learns the number, type, order, and magnitudes of transformations in an end-to-end manner, overcoming limitations of previous approaches that restricted transformation depth or relied on heuristics. Our extensive experiments demonstrate that FreeAugment achieves state-of-the-art performance across various domains by effectively sampling from all possible permutations of transformations without redundancy. Section: Method. In this section, we explore the method of data augmentation, which involves applying a series of image transformations to an input image, denoted as X. Each transformation, represented as tau, modifies the image based on a specified magnitude, m, which determines the extent of the transformation, such as the angle of rotation. We select these transformations from a predefined set of n possible basic transformations. We define our augmentation policy as a probabilistic model, P, which generates a sequence of these transformations along with their magnitudes, guided by parameters phi. These parameters are categorized into 3 groups: delta, pi, and mu, each corresponding to different degrees of freedom. For the depth of the policy, which indicates how many transformations we apply to a single image, we create a learnable distribution over possible depths. This is represented by a vector of logits, delta, where each element indicates the likelihood of choosing a specific depth. This results in a smooth probability distribution over the depths, which we can sample from. When it comes to the types and order of transformations, we sample a transformation for each augmentation layer. To avoid repeating the same transformations across layers, we treat this as a matching problem, aiming to pair n transformations with k layers. We learn a probability distribution for sampling a permutation matrix that represents this pairing, ensuring both rows and columns are normalized. To achieve this, we utilize a double stochastic matrix, DSM, which is a square matrix where each row and column sums to 1. We can convert any non-negative square matrix into a DSM using the Synchron operator, which alternates between rescaling rows and columns. Next, we focus on sampling from permutation matrices to learn the types and order of transformations. According to the Birkhoff-von Neumann theorem, the set of DSMs forms a convex hull for permutation matrices, allowing us to view DSMs as relaxed versions of these matrices. We aim to create a matrix of real logits that induces a distribution over permutation matrices, representing the assignment of transformations to layers. To handle the non-square nature of our logits matrix, we pad it with additional columns filled with very negative values, transforming it into a square matrix. We then apply the Synchron operation to this padded matrix to sample from the distribution of DSMs, truncating the extra columns afterward. As we sample, we note that these samples approximate permutation matrices. As the temperature decreases and the number of Synchron iterations increases, our resulting matrix approaches a binary permutation matrix. However, this process can lead to vanishing gradients and increased computation. To address this during the search phase, we select the index of the highest value in each column of our matrix. We also apply the straight-through estimator to learn the logits by backpropagating through the discrete choices of transformation types and orders. While this can lead to deviations from valid permutation matrices during evaluation, such occurrences are rare, and we find that repetitions of the same transformations across different layers are significantly reduced. Section Summary. In this section, we describe a method for data augmentation that involves applying a sequence of image transformations with varying magnitudes, governed by a probabilistic model that learns the types, order, and depth of transformations. We utilize techniques like the Synchron operator to sample from permutation matrices, ensuring diverse and effective augmentation while managing the complexities of transformation selection. Section: Degree of Freedom, Magnitudes. In this section, we discuss the degree of freedom regarding magnitudes. We build on earlier research that showed uniform sampling of transformation magnitudes performs similarly to more complex sampling methods, with the range of these magnitudes having a greater effect on the outcomes. For the basic transformation at the kth augmentation layer, we set the magnitudes to follow a uniform distribution within specified learnable lower and upper bounds. To learn these bounds through backpropagation, we use a differentiable approach for the transformations and apply the reparameterization trick. This allows us to backpropagate through the magnitude samples, which are calculated using a formula that involves a uniform random variable and a sigmoid function to scale the learnable variables into a specific range. We then adjust the magnitudes to fit the required input range based on the transformation. For transformations that are not differentiable, we utilize a specific estimator to assess the gradients of their magnitudes. Next, we describe our approach to policy search as a bilevel optimization problem. After establishing a fully differentiable method for sampling from our data augmentation policies, we follow the trend in differentiable data augmentation methods to learn the parameters by solving a bilevel optimization problem. This involves minimizing a validation loss while ensuring that we find the optimal training parameters. Instead of solving the lower problem at every step of the upper problem, we alternate the optimization of both sets of parameters using stochastic gradient descent. We replace expectations with estimates based on a batch of data samples, and we reduce variance by sampling a different augmentation policy for each image in the batch. This is made possible by an efficient implementation of our sampling algorithm. Additionally, Calculating second-order derivatives is manageable since the size of the parameter set is much smaller than that of the model parameters. In the experiment section, we outline our experimental setup and evaluation process. We compare our method to previous work across various natural image benchmarks and other domains. We also conduct ablation studies to analyze key aspects of our approach, demonstrating the effectiveness of FreeAugment and providing insights into its characteristics. For our experimental setup, we evaluate FreeAugment on 3 standard benchmarks consisting of natural images. We also assess its performance on a dataset with 6 different domains, totaling around 0.6 million images across 345 categories. We use a reduced training set for the 2 largest domains and reserve the remaining samples for testing. In line with previous studies, we employ specific architectures for the datasets. Section Summary. In this section, we describe our approach to sampling transformation magnitudes uniformly within learnable bounds and utilize a differentiable implementation to backpropagate through these samples. We also outline our bi-level optimization strategy for learning augmentation policies, which involves alternating updates of model parameters and policy parameters, and detail our experimental setup for evaluating the effectiveness of FreeAugment across various benchmarks and domains. Section: Baselines. In this section, we compare FreeAugment to a baseline that uses standard augmentations, such as random horizontal flipping and random padding and cropping for certain datasets, along with inception-style preprocessing for others. We also include various augmentations used for domain generalization, like color jitter, which adjusts brightness, contrast, and saturation, and random grayscale. Additionally, we compare FreeAugment to several existing methods, including AA, RA, Uniform Augment, TA, MADAO, SLAC, DRAW, and others. We designed FreeAugment's search space to optimize augmentation policies across 4 degrees of freedom, as shown in our figure. In our experiments, we explore augmentation policies with a maximum depth of 7. We use a range of transformation types, excluding identity and some others, which include shear X, sheary, translate X, translate Y, rotate, solarize, posterize, contrast, color, brightness, sharpness, auto-contrast, invert, and equalize. Most of these transformations have learnable magnitudes, which we detail in supplementary materials. We also apply cropping, horizontal flipping, and cutout by default, following standard training practices. For policy search, we conduct our searches on smaller data subsets, each containing about 10% of random samples, 5,000 images for certain datasets, 10,000 for others, and 6,000 images for 6 domains. We maintain a balanced train validation split of 50% to 50% and search for 300 epochs, using batch sizes of 128 and 64 for different datasets. We initialize the policy distribution uniformly and set the magnitude parameters to a normalized range. We use an optimizer for the learnable parameters, with varying learning rates for different aspects of the policy. To help the model learn before the search, we implement a warm-up period for training, applying gradual warm-ups for the magnitude, types, and depth. During the search, we scale Gumbel-based distributions with a temperature parameter that decreases from 1.0 to 0.5, and we set the number of synchron iterations to 20. We keep these configurations consistent across all experiments, demonstrating FreeAugment's robustness to hyperparameters without needing adjustments for different datasets and architectures. For policy evaluation, we assess the performance of the generated data augmentation policies across all datasets, replicating previous training configurations for a fair comparison. We provide all hyperparameters in supplementary materials for reproducibility. During evaluation, we set the number of synchron iterations to 20 and the temperature for Gumbel-based distributions to 0.1, as differentiation is no longer necessary. We report the top 1 test accuracy for each experiment, averaging results over 5 runs with different random seeds, and we denote the 95% confidence interval.